Hello and welcome to the first video in these AP Calc AB series. Today we're going to be talking about limits, and this is meant to just give a brief overview for a basic introduction into limits and what they are and kind of a few different ways we can calculate them. So how we think about limits in calculus is if we are given some function, that then when we take a limit, the limit is going to ask us, okay, if x approaches some value a, some number, what happens to the values of f of x, or the outputs? What happens to the y values? So that's really all a limit is asking. It's kind of asking us what's the behavior of this function. As x approaches some value, what happens to the y values of that function? So let's say we have the parabola. We're given the parabola x squared. So here we have f of x equals x squared. And I know that the point 2, 4 is on this function. So I know that we have the point 2, 4 on this function. Now what a limit might ask is okay, as our x values get really close to the number 2, what happens to our y values? What number do our y values approach? Now this is very different from asking what is the function output at 2. That's not what a limit wants to know. They don't want you to evaluate the function at 2. Instead, what a limit asks is, as we get really close, as our x values get really close to 2, what do our y values get really close to? And so we can see on this parabola that as our x values get toward that number 2, our y values are approaching 4. Now how we would write this using limit notation is we would say the limit of our function, which I've defined as f of x, we want to know what is the limit of this function as x approaches 2. So that's what this arrow here means. It's as x gets close to, or as x approaches 2, what is the limit of this function? So that is going to equal some value. And we already decided over here that that value is 4, because as x gets really close to 2, our y values on this function are approaching 4. So the limit of this function would be 4. And we could also write limit of x squared as x approaches 2, because we decided up here that f of x and x squared were the same thing. We just decided to call x squared f of x. So either notation works because we defined what f of x was, but you can also just put the equation right in there too. You can try another example here where let's say we had a line, and that line is going to be negative 3x plus 4. So we're going to have a y-intercept of 4, and we have negative slope, so that line is going to look something like that. So we have f of x equals negative 3x plus 4. And we want to know what is the limit of this function as x approaches negative 1. So to figure this out, we'd want to look at our function and go, okay, over here, let's say x negative 1 is somewhere right here. As x approaches negative 1, what do the y values on this function do? What do the y values approach? And so if we were to plug negative 1 into this equation, we would see that at negative 1, this line has a y output of 7. So this limit would be equal to 7, because that is what the y values here do. They get really close to 7. Now we have several ways that we can investigate limits, and here we saw that we kind of used a graph to investigate it, but there are a few other ways that we can look at limits. And those ways are algebraically, numerically, and graphically. And so algebraically is what we saw in the last example. That's when we plugged the number into a function. So if I had a function, let's say f of x equals x cubed, and I wanted to know what is the limit of this function as, let's say, x approaches 2. Then what I could do is I could plug 2 into this equation, and we can see that when we plug 2 in, we should get 8 out. So the limit is 8, because that is the y value we get out when we plug 2 into this equation. However, algebraically isn't always going to be the best method, because sometimes we're going to have situations where it might not work to do it algebraically, and so we will see that example. The other way we could also figure out a limit is with a table, and so this is the numerical way. So let's say that we have a table of values, and we are investigating the limit of some function as x approaches, let's say, 3. So if we wanted to investigate this and we didn't have the equation of the function, we were just given a table, let's say our values for x were 2.9, 2.99, and then over here we have 3.01 and 3.1. And then let's say that at this value, the y value is 6.9, here it's 6.99, and then here it's 7.01, and then here it's 7.1. And so we were given this table and we were asked to evaluate this limit based on the table. And so again, what a limit does is, as it wants to know, as x gets really close to this number 3, what happens to the y values. And so we can see here that the x values we've been given are really close to 3. These numbers are just a little bit smaller than 3, and these numbers are just a little bit bigger than 3. And what we can see with the y values is as we approach it from the left, the y values are 6.9 and then 6.99. So we're getting really close to what seems like 7 over here. And then if we approach it from the right, the y values are 7.1 and then 7.01. So these also get really close to 7. So by analyzing this table, we can figure out that as our x value approaches 3, as it gets really close to 3, our y values are approaching 7. And that is a way that we can figure out the limit of this function just based off of the table. The last method we have is a graphical approach, and this is where you might see a few interesting examples. So let's say that we had this function and we were told that at that point that value was 2, and right there that value was 3, and we were asked what is the limit, let's call this function f of x, what is the limit of f of x as x approaches 2. And we could look at this graph and say, okay, well our x values are getting really close to 2 over here, and as that happens our y values look like they're getting really close to 3. So just from that graph we could say that that limit is 3. But now what if we had a function and we put a little hole right there, and we'll still call that 2 and that 3. And so we'll call this g of x. And now if we were asked what is the limit of g of x as x approaches 2, this is where a lot of common errors are made, because as you can see right here we have a hole in this function. So this function is not actually defined at x equals 2, and that is called a removable discontinuity, which we'll talk about later in the continuity videos. And so when we're analyzing the limit here, it's a very common mistake for people to say, oh, well, this limit doesn't exist because this function isn't defined right there. But remember, a limit does not ask you what is the function's value at x equals 2. A limit asks you what are the function values, the outputs, get really, really close to as x approaches 2. So that's the difference. We're not actually asking you to evaluate it, just what do the y values get close to as we approach 2. And so the answer to this one is still going to be 3, because even though the function isn't defined there, as x approaches 2, from either direction, that y value gets really close to 3. So this limit is defined even though we have a removable discontinuity. The next situation that we might see is we might have a function that looks something like this. And so this is called a step discontinuity, where we have the function kind of piecewise here, and it's defined right here, but then this piece has removable discontinuity. So let's say that that's an x value of 3, and that is 4, and then we'll call this maybe 6 right there. And so this is where it gets a little bit different. So if we want to know what the limit of this function is, it's a little tricky, because as we approach it from the left here, it looks like our y values are getting really close to 4. But as we approach it from the right here, it looks like our y values are getting really close to 6. So this is where we actually define something called the left and right hand limits. So if I wanted to know what the limit of this was as x approaches 3 from the left, what I do is I put a little minus sign right here. And that little minus sign indicates that I'm talking about what is the limit as x approaches 3 from the left. And then likewise, if I wanted to talk about the limit as x approaches 3 from the right, I would put a little plus sign here. So this specifies which direction you're coming at it. So let's call this function h of x. So I'm taking the limit as x approaches 3 from the right of h of x. And so, excuse me, that's the left. So if we're taking the limit as x approaches 3 from the left of this function, we can see over here that if we're coming in from the left, it looks like those y values are getting really close to 4. So we would say this limit is 4. But if we're coming from the right, we can see that the y values are getting close to 6. So our right-hand limit would be 6. And so you might ask, okay, well then what's our kind of, I call it, not a scientific term, but I call it the overall limit. So what is just the limit as x approaches 3 of this function? Sorry, that should have that right there. So what is the limit as x approaches 3 of this function? Not from the left or right, but just overall. And so this actually is not defined. So I'll say does not exist because our left and right hand limits are in disagreement here. Our left hand limit says that our y values approach 4, but our right hand limit says that our y values approach 6. So when they don't match like this, we can't say there's a overall limit. It doesn't exist because these two limits have to be in agreement. We can talk about the limit from the left and from the right, but they don't match, so we don't have an overall limit here. Another situation that we could come across is if we had a removable discontinuity right there, and then we had that. We'll say that's 6, call that 4, and then we'll make our x value 2 here. Call this g of x. So now in this situation, if we want to think about the limit of g of x as x approaches 2, this is another common error that happens. So a lot of people will look at this and go, okay, well, right at 2, the function is defined at 6 because we have this point up here. So the function right at 2, the y output is 6, but that's kind of an outlier, that point right there. And so if we think about a limit, sure, if we were to evaluate g of x at 2, that would be 6. But a limit, again, is not asking you to evaluate it right at 2. It's asking what do the y values get really close to as x approaches 2. And so if we look, if we see as x gets really, really close to 2, it looks like our y values are going to approach 4, right? Because this is kind of a jump right here. If we're just thinking about the pattern coming from either side, we're getting really close to a y value of 4. So this limit is actually going to be equal to 4, because again, it's that as we approach to what happens. One of the last situations with limits that we might see is limits involving infinity. So let's say I have some sort of decreasing exponential function here, call it f of x, and I want to know what is the limit of f of x as x approaches infinity. So I want to know what the limit of this function is as x approaches infinity. So here, this is kind of asking us to think bigger picture and look at the end behavior. So as x goes to positive infinity, so we're moving to the right here, what happens to this function? Now, I didn't give you the equation of this function, but this function is going to decrease and have a horizontal asymptote right at the x-axis. So that means this function is going to get really, really close to y values of 0, but they're never actually going to get to 0. So we would say that the limit of this function as x approaches infinity is 0, because it's approaching y values that get close to 0. We can also think about if we have a function like the square root function. So f of x equals square root of x. And we can ask, what is the limit of this function as x approaches infinity? And unlike the last function, this one does not have a horizontal asymptote. It is not getting really, really close to some value. This function actually is going to grow unbounded in this direction. So this function has no limiting value. It's just going to keep getting bigger and bigger, and the y values are going to keep getting bigger. So this function actually has no limit. So you could say the limit doesn't exist, or the limit is infinity, but I'm going to say that this function has no limit, because it's just going to keep on growing and it's not going to stop. There is some discrepancy between which is the best to say Should you say a function has no limit? Should you say the limit doesn't exist? Or should you say the limit is infinity? Generally, especially on the AP test, any of those should be fine, and most teachers will consider those to be the same. Some teachers are a little bit picky about the language. You should be able to say any three of those and they should be fine, but you can always check with your teacher and see if they have a preference. The last situation we're going to look at is we're going to have a function that has a vertical asymptote right at 4. And this function is going to be 1 over x minus 4 squared. Now I'm going to ask you, what is the limit of this function as x approaches 4? And so this one's interesting because, again, it's growing unbounded. It's going to keep getting bigger and bigger and bigger on both sides because it has this vertical asymptote here. So it's going to keep getting closer to that vertical asymptote, but it's never going to actually touch it. And both sides are going up toward positive infinity. So this would have, again, no limit or does not exist, or the limit is infinity. So I'll write does not exist. Now, if you were to try to evaluate this algebraically, like we talked about at the beginning, where we plug in whatever number we're trying to evaluate this limit at, then if you plugged 4 up here in for x, then you would see you'd have 4 minus 4, which would go to 0. 0 squared is 0, so you would end up with 1 over 0 if you try to use the algebraic method to evaluate this. And as we know, we can't divide a number by 0. So if you end up with a situation like this, it's good to maybe think about what the graph looks like or try to draw a picture to see what's happening. And because the reason you get that undefined is because there's no limit, it keeps going to infinity. Now, there's something that doesn't come up a lot but is worth talking about. If we have the function 1 over x, so this is 1 over x. And I asked you, what is the limit of this function? So the limit of this function as x approaches 0. And so if you were to look at this, as x approaches 0 from the right here, we can see that this is going to keep increasing. This has a vertical asymptote at the y-axis. But down here on this piece, this also has a vertical asymptote of the y-axis, but this piece is headed towards negative infinity, right? The y values are going to keep getting more and more negative. But up here, these y values are going to keep getting more and more positive. So which one would it be? Because here from the right, it grows toward positive infinity, but from the left, it grows towards negative infinity. So this is another situation where there would be no overall limit because the limit from the right and the limit from the left are in disagreement. So you could say that the limit of this function as x approaches 0 from the left would be negative infinity. But you could not say that about the right, because from the right it approaches positive infinity. So that's a situation that you want to be careful in, because we cannot say that there is an overall limit for this one. There are some properties for limits that are also good to be aware of, some algebraic properties that will be useful. So one of those is if we have a limit and we're taking the limit of k times some function where k is just some sort of constant, it's just some number, that is equal to k times the limit as x approaches a of that function. So you can see here that what I did is I moved the k out front. So if we had something like the limit of a function as x approaches, say, 3, and we made k 5, that would be the same thing as pulling that 5 out front and taking the limit of that function as x approaches 3 first, and then multiplying it by that 5. So that simplifies your computation a little bit and allows you to take the limit, evaluate that function first, and then multiply it by that 5. Another property that we have is if we have the limit as x approaches a of f of x plus g of x, we can also split that up. And we can say that that is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So this also allows you to find each limit separately and simplifies your computations a little bit. The last property that we have is if we have the limit as x approaches a of f of x times g of x. That is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. So again, whenever you have this kind of composite functions, two functions put into one, and you're trying to find the limit of them, we can split it up and calculate each limit separately. And so that is it for this general overview on limits. Hopefully this was helpful. If there's anything you'd like to see, any comments, improvements, please let me know, and make sure to subscribe.